All right, let's talk about other ways, other things that we want to be able to model. For instance, aggregation, composition, and generalization. Uh, so, so attributes can be multi-value, can be single value, right? They can be arrays, or they could be simple data types, strings, numbers, floats, dates, whatnot. And we need to be able to capture these things, right? Usually, in object-oriented programming, you have lists and collections and all these higher level data types that usually have no equivalent in a relational database. So here's a couple of things that we might want to be able to capture, right? That we have an order that is keeping track of an engine that we're selling, right? And also we might have a car that also has a reference to that particular engine, and the car might have a reference to wheels, right? And here we're specifying that with a diamond, right? We're specifying that there's a particular type of association between these two, right? We're saying that there's an aggregation relationship, right? That the order might have multiple engines, right? Or might have a particular engine that is pointing to. It's not specified here how many, right? On this side, though, it is implied that this could exist or not exist, right? That this could be a 0 to 1 relationship, right? And one thing that is peculiar about what we refer to as aggregation is that it does not impose any particular life dependency between the two, right? Meaning that if one of them exists or one of them disappears, then it doesn't imply that the other has to disappear, right? So, for instance, if I remove the order, right? If I remove the order, well, that doesn't mean that the engine should disappear, right? That I have basically I have a reference to it, right? I have a reference to it. I'm pointing to it, right? But my existence does not determine the existence of someone else. Okay. So that's what yeah. There's no life cycle dependency between the two, right? As opposed to as a composition. In composition, if the person dies, I guess this is a very macabre example. Uh, where that let me think of something better. So for instance, if my main mental model of my existence in Facebook is that I own everything, maybe not. If I have a tweet on Twitter, or I have a post or upload a video or picture, my mental model is of a composition relationship, right? That if I leave, right, then I don't exist anymore in the platform. My mental model is that all my content would also go with me, right? It would not exist anymore. Now, Facebook's mental model might be different. It says, no, this is an aggregation. Okay, you leave, we keep everything, right? So again, it's a business decision of what you mean, of what you understand, what the life cycle of something, depends on the life cycle of something else, right? That and sometimes it makes sense that this composition, sometimes it makes sense as aggregation, right? For instance, you have a web page, and a web page might have all sorts of widgets inside, right? And maybe each widget is represented as a different record, right? And the page itself could be represented as a single record. And there might be a many to many here that says, I'm sorry, a one to many, saying that one page has many widgets, yes? Now, if I remove the page, would it make sense to keep track of all the widgets? Probably not, right? That if you remove the page, it makes sense that you remove all the widgets, right? But say we go a little further up and says, okay, you have a website, right? And the website has many pages, right? And then if you remove the website, does it make sense to remove all the pages? So, well, maybe, right? Maybe. Does it make sense to keep a page if the website goes away? Well, maybe not, right? Let's go a little further up. It says, well, a lot of folks are working on that page, or maybe you have an author of that page. If the author leaves and remove the record, do I remove the page? Do I remove the website? Well, maybe not, right? So probably that's an aggregation, where all the other ones were compositions, right? So the dependency of whether the life cycle of one depends on the life cycle of the other, that's what we mean by composition. Make sense? Or aggregation, all right? And you document it using this filled in diamond or this empty diamond. Yes?
How to decide where the diamond will be placed
On the weak side.
on the weak side?
Sorry, on the strong side. Strong side, yes. And a lot of folks don't even use this notation, right? It's only when you explicitly want to document that there is this particular life cycle dependency, okay? Right? Oftentimes it's interpreted that on this side is a one and on the other side is a many. It's implied. Oftentimes it's not put on the diagram, but it's implied as a one to many. Other relationships, such as generalizations, right? That we want to have, like, we want to be able to capture some fields or some concept or attributes that are common to all sorts of different entities, such as, for instance, you might have a professor, a student, but they all have certain things that are in common. We have first name, last name, date of birth. We all pay taxes, so we have a social security number. So all those things that are in common with everybody, we would capture it in some generalization, and then we can inherit these attributes down below. The problem with this with implementing generalization is that there's no equivalent in relational databases, right? Relational databases do not have a means of capturing relationships, inheritance relationships. Nevertheless, we want to be able to see, how could we capture this data, right? After all, we're selling you the idea that you should do all your diagramming, do all your design at a conceptual level, and then convert to a relational database. That we're selling you that. So here's an example of a person, professor, and a student, right? And so here is a proposed way of implementing it, right, in a relational database, right, where you have a per class, you have a per table, right, where the person, you have the primary key, yeah, you have the name, the age, and whatnot, and then you have the professor and the student. Conceptually, they're inheriting from this base class, right? This base table doesn't exist, right? A base table. And notice that they only capture those fields that are specific to those tables, right? To those classes. Yes, right. But they also maintain a one-to-one relationship with their parent, right? Their primary key is also a foreign key that goes to the base table. See that, right? Same thing with the student, right? And there would be a composition relationship here, right? That if I remove the person, right, the professor and student goes with me, right? There's a one-to-one here, right? That I've only split the information of the professor between two tables. Half of the information lives in the professor table, and half of the information lives in the person table. See that, right? If I ever want to retrieve an actual professor, I will have to join these two tables, right, to have the actual representation of the professor. And same thing with the student. I'll have to join the student table with the person table, right, to get the actual representation of the original student. Make sense? Okay. This is just one way of doing it. There's two or three more. We'll talk about them a little later when we talk about ORMs. Yes. Okay. Yeah, there's a, yes. One to many. Yeah. No, one to many. Oh, okay, I have to change it. So the schema implementation, we'll see that in a minute. So here's another example of going the TA inheriting from the student, having a many-to-many with a course. Here's another student, many-to-many with a course that is registered. So let's look at implementing some of these. So here we have the faculty, right? The table for the faculty, there's a one-to-many. So the course is going to have a foreign key to the faculty, right? Here's the course having a presumably a foreign key somewhere. Taught is not, no, okay, not yeah, taught by points to the faculty, right? That's the one-to-many. And here's a generalization, right? We have the base student, right? We have the base student. We have the TA that is inheriting from the student. So here's the base student, right, with its primary key, the name, right, and then we have the primary key of the TA, not only being a primary key, but it's also a foreign key, right, that is referencing the student. Okay, so there's a one-to-one. So if we ever want to know the information about the TA, we're going to need to join these two tables, right? Here's a here we're an example of reifying the many-to-many between the student and the course, and then we're going to reify the relationship between this course and the TA. So here's the reification of the assigned, right? The reification of the registration, right? Here's another example. Vehicles are parked in a garage. Every garage has an address. Some vehicles are cars and some are boats. Every vehicle has a unique VIN number. So we're looking for these things, right? We're looking for these has a or is a or special case of something else, right? Has an owner, is a, right? So here's a diagram of a car, boat. Both of them being vehicles. A garage having many vehicles parked in it. And here's the table, the garage table. The garage table having a one-to-many relationship with the vehicle. So the vehicle points to the as a foreign key to the garage. And then here we have the base class vehicle. The base class vehicle then inherited from the car and the boat. Notice that both of them have a primary key, but then the same primary key is also a reference foreign key to the vehicle. Right? So there's a one-to-one relationship between the two. So these are subclasses. Again, this is one of two or three more ways of representing this. Yes?
Do we need to totally understand this code?
Yes.
I'm not quite familiar with
Okay.
this language. What is this language?
Yeah, so last week we talked about SQL a little bit. We talked about the create statement.
Is that SQL?
Yes, yeah, it's SQL is a create statement that allows you to create a new table. Yeah, yeah. So let's go over that real quick. Right. So these are graphical ways of representing the data model. Yes, and we talked about algorithms that allowed us to represent this visual representation into a schema, into a relational model. And what we mean by relational model is relational databases, right? That we're implementing tables. We're implementing tables using this language, the SQL language, that allowed us to create a table with a particular name and the fields in that table. And each table, each field, we could determine what data type there were: integers, doubles, strings, varchars. And also the primary keys that allow us to uniquely identify each record, such as parked in as a foreign key to the garage. We'll go over this and look at this for the next month or so.
Hi everyone, Jose here. Please remember to subscribe and like the video, and if you have any questions, please leave a comment down below. Thank you.